right. I'm with the South Dakota Mesonet. I am. Me and the other the other 4 states here from North Dakota State University, University of Wyoming, University of Montana, and University of Nebraska-Lincoln. We all operate Mesonets and have been operating Mesonets, some of us for since the early 80s. To give a quick background to this, there was major flooding in 2011. It damaged, there was significant damage. There was, right following that, a major drought the next year. And then in 2019, there was another major flood. And after the 2011 flood, the Corps of Engineers had a third-party review done of what it needed to do to handle this type of situation in the future. One of those things that this third-party review focused on was the fact that the plains in the upper Missouri River Basin were not, there wasn't enough data on soil moisture and snowpack. So that's where we came in. We already had stations out there and we had the ability to put in more. So these, I don't know if you can make it out, but this is made up of a bunch of 500 square mile squares, and there's 540 of them total. And our goal was to get a station in every single one of those. As of the end of this field season, we should have 173 in total across the states. We're due to complete in 27. This is an example of one of the stations. We're doing temperature, humidity, 10-meter wind, solar radiation, precipitation, year-round precipitation, which was an expensive but important upgrade for this, of course. And then snow depth, soil moisture, soil temperature, and a weather camera. I'll get into that a little more. And the focus here is total water monitoring. So we wanted to get at things like, the year-round precipitation. So most of us started out as ag weather networks, and we get the majority of our precipitation on the plains in the spring and summer. And that's primarily what we were focused on, and unheated tipping buckets were fine for that. For this, we needed to upgrade to weighing gauges. And also we want to get at ET, we want to get at snow water equivalent. So we get a lot of values that can contribute. If you're familiar with the SNODAS model, that's what the Office of Water Prediction and NOAA uses to come up with their SWE. And that, basically everything on the station is built to support that model, or the Sacramento model, or the drought monitor. So that to continue here, we've got of course soil moisture, and then actually I usually just say soil moisture. The temperature is a big part of it too, because we've got, if the ground is frozen, we've had years where when the ground is frozen, it's as good as saturated, and it just, when that snow melts, like say you get a rain on snow event or something like that, it just goes right off, and the ground, even if it's got the capacity for it, if it's frozen, it's not going to infiltrate. And then we also do snow depth. So these are kind of the supporting actors: wind temperature, solar radiation, and humidity. That's a pretty awful image, sorry. That's most all of them, this is the weighing rain gauge. It's they're all shielded, and most of them have heated rings. We're using the TDR 310N in South Dakota. We tested. There was a test bed done before this. So there's long periods of soil moisture record in some of these states using particular types of equipment. And in those sense, like as long as they tested well with each other in the test bed, then it made sense to continue to use those in those states. Here's an example of what the weather camera is. You know, it's mounted on the mast for the solar panels, and it looks down. I want to point out a few things here. Well, actually, this one doesn't have it yet, but typically, like what we like to do around our stations is get 100-foot buffer in any direction from the station. And we just leave that as grass, or once we get the weeds under control, we leave it as grass. That is important to get. I mean, we're out on the plains. It's very windy. It's really hard to get a snow measurement. Anybody who's tried to measure snow knows how difficult it can be. So as the station, like this one would have gotten seeded next, and then that 100-foot buffer would grow up. I mean, somebody asked like what we were looking at for an ideal height. I mean, somewhere around like 18 inches or something like that. Seems to do a really good job of getting even drop of the snow. So this arm hanging out, that's a sonic snow depth sensor. And then you can see there's a white snowboard below it. What the camera is really doing here is we're able to see a lot of things, like what you can see at the bottom by the snowboard is like basically a glorified yardstick. And so we can, you know, if we suspect there's some problem with the snow depth sensor, we can read what we're getting from it in the data, and then we can compare it to that to see if there was issues. So it's a quality assurance type of thing in that respect. We can also see if the snowboard is representative of the surrounding area or not. This was not part of the design criteria, but one thing that I'm looking forward to using it for is for drought monitoring. We're going to have, I mean, especially this is not, there's never crops right up against these. So it's just the same grass every year. And so what we'll be able to do is see like, when do things green up? When do things dry out? I mean, that has implications for fire weather, for drought monitoring, and so on. And then actually the Weather Service, the forecast offices love these for keeping an eye on severe weather. So a really important part of this project is the soil sampling. I want to call out Dave Hoover here. His lab, the Kellogg Soil Survey Lab, has been, like, our local NRCS people have been going out into the field, like what you see here, and they get a pit done and they take samples. They do some observations in the field, and then they package them up. I don't know if you can see them on the clods on the string there, but they get sent back to Dave's lab, and we get an abundance of data from them that is really important for some of the stuff I'll talk about in a bit. So these are kind of, I won't go through this one by one, but basically we're looking at things that can get us that fraction available water, and that can get us also some variables that are used in the Sacramento model, including a way that we can, if you're familiar with the Sacramento model, it does depth. It does have two different layers of depth, but they're not physical, they're bulk. And having this type of information allows us to assign a depth at any particular station to that depth between the upper and lower zones. Oh, yeah, and I did mention thaw depth and frost depth earlier. These stations shouldn't be ignored for that. If you're in anywhere that it freezes, the impact on the hydrology is significant. So anyways, I also want to cover here the NIDIS mapping project. Ronnie and myself and Laura Edwards are working with Marena and the drought.gov team to get this out there, to make it, you know, kind of what Tyson was getting at is, you know, to be able to communicate it out to people, have it and get it used, you know. One thing there, somebody else was pointing out that the drought monitor doesn't get, I mean, there are complaints all the time about when lines move. And one thing that we're aiming to do with this mapping project is make it more transparent as to what the data says, you know, what the data, some of the things that the decisions are being made off of to draw those lines. And I think, so we're not just looking to improve the drought monitor, but also to show to both contributors and stakeholders where that's coming from. So you might be familiar with the archive maps at the Drought Monitor website. This is kind of how we're launching, or I mean, we're going off of this basic format as far as like selecting area and time frame and stuff like that, to try to line up with a lot of different user needs, but in particular the drought community. There's some things that we've tried before. This is what we have on our website for soil moisture. This is called the poker chip map, where you get all 5 layers. Right now, we only have that in volumetric water content, but in the future, we'll be able to do that in available water. When you stack those poker chips, I mean, those same colors, and you do a time series with it, we do what we call our layer cake. And so here you can see the gray is the frozen soil layer. And you can, and then on top, I should point out the purple lines are precipitation. So you can see when that hits that, you know, you can see how much it infiltrated. You know, some of those got down to the 8-inch, some got all the way down to the 20-inch or even to the 40. So I think this kind of stuff can be useful, especially if you want to know the history at a particular station, if you can go on the map to something like that. Then I've just got some, there are lots of other applications for these cameras. This was the derecho that went through Brookings. It's a sequence of it moving in. Actually, the next image after this, it was so dark. This was in the middle of the day. It was so dark, it went into infrared mode. You can capture stuff like this. This is what pretty much everywhere in South Dakota looks like. And this is a cell that went over Bear Butte, which is a famous place in our state. I want to thank the Corps of Engineers who's funding the stations. National Weather Service is funding the ongoing annual funding for the stations. NIDIS has been a partner all along, and the NRCS, like the local teams that collect the samples, the lab that does the analysis, and especially my crew. I've got a really great crew, and all these stations are put in top notch. So.
Great, thank you, Nathan. We have a few minutes for a question or two.
Thanks, Nathan. Great talk and great progress. Great pictures too. I wonder what camera system you all are using and how that's been working for you.
I get quite, he asked about the camera we're using. I get questions on that a lot. We're using a recently discontinued camera system, so which the turnover in cameras is like, I mean, we complain when a sensor that's been made for 40 years is discontinued. So we just, you know, we could kind of carry that expectation onto cameras, which is not realistic at all. But the short answer is, I think we're going to move to just HD level dumb bullet cameras and put 4 of them at each station. And then try to, I mean, any particular model will be discontinued, but that's, you know, that's one that's pretty replaceable without, they're low cost. I see these cameras as more or less disposable, like as far as technology goes. And I mean, there, one benefit to doing that too is you can get the view all the way around, and you, which is good for the drought monitoring aspect of it, and then also for the weather spotting aspect. But I think if you get too invested in one thing that has really particular quirks to it, it's going to just be hard to keep up with things being, you know, putting them going into obsolescence.
Any other questions?
Hey, I was curious how that precipitation gauge worked. You said it was heated with rings.
Yeah, so it's for like a $6,000 setup. This is really demeaning, but it's basically a bathroom scale with a 5-gallon bucket on it. And you put antifreeze in the bucket, and then that's all got a shroud over it. It's got a 400 square centimeter opening, and the rim of it is heated to prevent accumulation. It really happens with wet snow. Although in alpine areas you can get like icing on it too, but at any rate, that's heated to keep the, you know, that wet snow from getting on there. And yeah, so and then it just weighs the precipitation, which is how you get both the rain and the.
What are the power requirements for something like that?
I'm sorry.
The power requirements for heating it?
Yeah, so I get asked about the power a lot. The camera and the heating are the big things. We've got, I think, 720 watts of solar. So, and I don't remember the battery sizes right off, but it's a significant amount of power there. And we're probably have more than we need, but I have never downgraded solar power on a station. I've only ever upgraded, and leaving a little bit of buffer there, you know, for some sensor I can't even think of right now. Like if we decide we want to add that later. I mean, we do have some. The other thing is the camera. The cameras use up a lot actually in 3 ways. Like, I mean, they're kind of power hungry on their own, but when you fire up the infrared if you want to get night photos, then they get really power hungry. Plus, the modem has to be on a lot more, you know. My kids send more in text messages as far as data is concerned than the rest of the station does, you know. But I mean, once you start sending photos, it adds up.
Thanks.
Are we out of time? All right.